All right, section 13.8, constraint optimization and Lagrange multipliers. We started this last time, so let's just kind of rehash where we were, and it's been a little while since we've looked at this. We talked about the fact that the basic idea is that you have, sort of in your mind, you can picture it this way. You've got a mountain range and you've got a road along a mountain. And our real question is, along the road, where do we have maximum and minimum values occurring? And so we used the Lagrange multipliers and explained a little bit of how they worked by doing an example. And the example we did was kind of lengthy, but it was finding the minimum or the point that was the minimum distance away from a specific curve. And in this case, it was a line. So we had the line y equals x minus 2, and we had the point 0, 2, and we want to minimize the distance to that point. And so along the line, but to the point. I think I said that right. We talked about that. The Lagrange multiplier equation is down here. It's taking the gradient, which was the partials, and setting them equal to each other with a factor of lambda in there. It's a constant multiplier. And in doing so, we actually found that the closest point was the point 2, 0. So that's where we were last time when we ended this particular problem. All right, there was the homework. You guys have that written down, and I'll just leave it there for now. So I'd like to take a look with you at how this is sort of used in general, because that was a very specific application. Find a point on the curve that is the nearest point to another point. I mean, like that's very specific. Obviously, this must be used for something a little more generalized than that, or it's sort of limited in its applicability. So we're going to take a look at theorem 8.1, where I'm actually, and it's got a definition within it, so it's a definition theorem combo. That's what you get today. You get a combo. And theorem 8.1 has the details of how this works. So we're going to suppose that f of x, y, z and g of x, y, z are functions with continuous first partial derivatives. And the gradient of g of x, y, z does not equal 0 on the surface g of x, y, z equals 0. So the derivative, the gradient anyway, which is these partials, is not equal to 0 when the surface is actually equal to 0. So suppose that either number one, the minimum value of f of x, y, z subject to the constraint g of x, y, z equals 0 occurs at x0, y0, z0, or we're going to write the same statement, but we're going to put the word maximum in it. So the maximum value of f of x, y, z subject to the constraint g of x, y, z equals 0 occurs at x0, y0, z0. Okay, so that started out as suppose that one of these two things happens. Then the gradient of f of x0, y0, z0 equals lambda times the gradient of g at x0, y0, z0 for some constant lambda, which is called a Lagrange multiplier. Lagrange was a mathematician, so that's why that is capitalized, just in case you're wondering. It's a Lagrange multiplier. This gives formal structure to what we had written last time, sort of in the margins, if you will. We've got this equation that we can use to find maximum and minimum values. So if there is a maximum or minimum value, then it's going to satisfy one of these conditions. That's what we're looking for. All right, so the question is, how do we use this information to actually find these maximum minimum values? So I don't always do this in mathematics because sometimes it's better to just move through things intuitively, but I am going to go with it on this particular one. I'm going to give you a little bit of a sort of a procedure on how you go about doing a problem like this, okay? So the first thing you have to do is you have to set up your g of x, y, z equation. The second thing is to find the gradients. So find gradient of f and the gradient of g. Whoops. There we go. The third thing then is to set the gradient of f equal to lambda times the gradient of g and solve. Well, let me say it this way. And eliminate lambda first. And in eliminating lambda, we solve it. So maybe I'll just write that over here too, just for kicks. All right. Number 4 is that you use the solution from step 3 in the constraint. Because everything is happening along the constraint, along the curve, along the road, if you will, to solve. And then number 5 is to verify which one or ones is or are the max-min. We may have more than one solution. We need to figure out which one actually is the solution to the actual problem, not just satisfies the conditions up to that point. This is sort of a step-by-step description of what we're going to do. We're going to do a couple of examples of these. The first one we're going to do is a example with 2 input variables, x and y, and then the next one we're going to do is going to have 3 input variables, x, y, and z, so that you can kind of see the structure of how it looks a little bit different. They aren't drastically different, but I want you to see them both. Ready to take a look? Okay. Here's our example. No idea why I'm using red. How about we use some black? going to use Lagrange multipliers to find the maximum and minimum of the function f subject to the given constraint. And our function on number 2 is f of xy equals x squared e to the y, subject to the constraint x squared plus y squared equals 3. Okay, so what was the first thing we're supposed to do? We need a g of x equation, and we don't have it exactly yet. G of xy is a very simple equation to get. You get it from the constraint. All you're doing is you're moving everything to one side so that 0 is left on the other side, and that's what we're going to call g of xy. So on ours right here, I'm going to go with x squared plus y squared minus 3. If you wanted to do 3 minus x squared minus y squared, that's fine too. Won't hurt anything. You'll get the same solution. Okay? So that's step 1. Step 1 done was 5 steps, so right, 1/5 of the way there, or something like that. What's next? Gradient. So what is the gradient of f? Right, okay, so the gradient of f is going to be f sub x, f sub y, like this. So we need to find those particular values. So what is f sub x for our function f of xy? Perfect, 2x e to the y. Now we need f sub y. Okay, is everybody good with that? All right, now as a general rule of thumb, and this doesn't have to be true, but as a general rule of thumb, the constraint is usually easier to take the partials. There's usually a clearer kind of a curve given there. And so when we do our partials with respect to g, they're quick, they're clean. I didn't write that right, so let me try that again. All right, so what are my partials? What is my gradient of g? Right, 2x, 2y. Step 2, done. Right, find the gradient. Step 3 is to set up the equation, basically, that the gradient of f is equal to lambda times the gradient of g. Now, the reality is what we really want is we want to do this sort of piecewise or component-wise. So if we take the x component, we're going to have 2x e to the y equals lambda times the x component of g, which is 2x. And we're going to do the same thing with y, so we're going to have x squared e to the y equals lambda times 2y. Take a look at that first equation that I wrote, that you wrote. What do you notice? Yeah, they both have a 2x on each side, so those are not helping me out in terms of simplifying this. I can get rid of them. So lambda is actually equal to e to the y, right? So I can use that value for lambda into this equation, and I can eliminate lambda. I'm substituting is what I'm doing. Now, if you see something that you want to cancel here in a minute, we'll do that too, but we're going to substitute first. So we have x squared e to the y equals e to the y times 2y. Then what? Yeah, in very much the same way that e to the y's are going to go away, right? So we actually find out that x squared is equal to 2y. So that is all for step 3. We're not actually getting numerical values in step 3. So when I put over here in parentheses solve, the eliminating of lambda usually gives me some kind of an equation as a solution. X equals something about y. That's our idea. And the reason we want that is because in step 4, what we're going to do is we're going to, plug that into the constraint. So the constraint was back way up here, x squared plus y squared equals 3. And so we can either replace the x squared with 2y, or we can replace the y and solve for y. Which one's going to be easier given the sort of the structure that we already have? Yeah, replace the x squared. That's going to be the easier option, right? Okay, so I can actually write this then. So into the constraint, let me write down what the constraint was just to remind us. X squared plus y squared equals 3. And so x squared is 2y plus y squared equals 3. So how are we going to solve this now? Okay, let me move to the next slide. I think I'm out of space here just a second. There's one other thing we're going to have to go back and make note of. I skipped over it, but we'll get there. All right, so what did you say to do, James? Okay, so tell me what to do. Complete the square. We could do that. Is there something easier? Yeah, we could move the 3 over. This one actually factors.
It should be 2y squared.
Yeah, it should be 2y squared.
Or it should be, sorry, 4y squared, yeah.
Should it?
X squared equals 2y.
Oh, no, just kidding.
Okay. That's all right. Be careful, right? Because it's actually x squared that gets replaced with 2y, so it's not squared. So we actually can, in fact, factor this one. So 2y minus 3 equals 0. So, Tal, you're the one who told me to factor. Did you already factor it? Y minus 3? Okay, y plus 3, y minus 1. So we have an option of y equal to 3, negative 3, or y equal to positive 1. And I need some x values that go with those, right? And you can use the fact that you knew over here that x squared is equal to 2y to figure out what x would be with those corresponding y values. So if y is equal to negative 3, what happens? Yeah, that's not going to work, right? So this is not really an option. I would get imaginary numbers to try to get for x, and we're working the real number system. What if y is equal to 1? X is what? Plus or minus, right? Yeah, so we get 2 solutions out of this one. We get, square root of 2, 1, and negative square root of 2, 1. Now there's one other thing that we need to do. We need to go back and catch on this. I didn't touch base on it when I did it. But when we eliminated over here the x, the 2x, and I'll tell you why it doesn't happen with the 2y's, or the e to the y in a moment, we actually eliminated a possible solution. What option was really there that could make this all work? Yeah, that's an option of x equals to 0. If x is equal to 0, we would get 0 on both sides as well, correct? And so that would be a legitimate option as well. So if x is equal to 0, then what would y equal? You can do it based on this, because this is contingent upon x not being 0, so you can't use this equation. This doesn't work. Y equals what? No, we need to use the constraint equation. Yeah. Right, so y is equal to plus or minus the square root of 3. The reason we can't use this equation over here, that we got x squared equals to 2y, is because that was hinging on the fact that x was not 0. The only way that ever can occur is if x is not 0. Now, why do I not have to worry about this issue when I eliminated the e to the y's? Okay, but why can I just sort of remove it and not have the extra what happens when this is equal to 0 business? I mean, is e to the y, if let me say it this way, if e to the y equaled 0, would both sides equal 0? Yes, but e to the y can't equal 0. It's an exponential. Exponentials are always above the x-axis. They have a horizontal asymptote that is the actual, y-axis. So that one doesn't ever give me 0. Are you with me? So we're looking at any possible way that both sides could actually be the same. So if e to the y were 0, that would work, but that's actually not a possibility because of the function that we're dealing with. All right, so we actually ended up with, I believe, 4 points, right? We also had, 0, square root 3, and 0, negative square root 3. So I have 4 possible points where I could have maxes or mins. That's what this says. Everybody good so far? Where are we on our list of steps? We're on 5. Fantastic. Verify which one actually works, basically, right? So any idea about how we would do that? We're going to do what we did in the last section. We're going to plug it into the function f, right? So we're going to plug in, f of square root 2, 1, f of negative square root 2, 1, f of 0 square root 3, and f of 0 negative square root 3. And our function, which I don't even have on this slide at this moment, is x squared e to the y. All right, so let's do, how do we do the bottom two first? Because those are the easy ones. What happens when x is 0 and y is square root 3 or negative square root 3? These are both zeros, right? Because I've got x is 0. What if x is actually square root 2? I get 2 e to the 1, so what's that? 2e. And how about the other one? 2e. Hang on just a second. Okay, so looking at this piece of information, which ones are max, which ones are min? Or what can I say at this point? Because that's what I'm looking for. Okay, so we have a max of 2e at 2 locations, right? At square root 2, 1 and negative square root 2 of 1 and 2. Negative square root 2 of 1. And then I have a min of 0 at 0 square root 3 and 0 negative square root 3.
Is it proper to put inputs as positive negative square root 0?
Yeah, you can do that if you'd like. I don't have a problem with that. I want to mention one thing. When I actually did this in my notes, I have no idea why I chose the hard way to do it, but I actually did the replacement the other direction. So when we substituted the 2y in for the x squared, I actually solved it for y. It was probably because I was modeling after some book problem or something like that. And I get the same answer at the very end, but there's one little piece in the middle that actually created another point that I actually tested, and it gave me something that was a value between 0 and 2e. It gave me a value of 2 over e as a possible extreme value, and it's actually a number that actually occurs between 0 and 2e, so it actually does neither. So you could get an answer from these, descriptions here that is a neither answer as well. So just to be aware of. All right, any questions on that one? Okay, let's try one more. Same idea. I'm not going to rewrite the directions. My function f is going to be f of x, y, z this time. And this function is x minus y minus z. And it is subject to the constraint x squared minus y squared plus z squared equals 1. Oh, you know what? Write that down, and I want to draw your attention to one other fact from the last problem I didn't mention. Does everybody have that okay? If you take a look at this particular equation, the constraint on this is not a line. When we were doing the very first example in last class session, my constraint was actually a linear equation. It was a line that I was lying along. What is this equation's constraint? It's a circle. So I'm actually looking sort of at a circular region. So if you imagine sort of having like, a road around a mountain, and it doesn't work exactly because if we had a road, it would also have, be going up and down. This one's actually level, so it's just a walking path. Let's say it that way, a walking path around the mountain in a circular pattern. Okay. This one, I actually have a 4-dimensional shape now, so we can't even talk in 3 dimensions and make sense of that quite the same way. But I do have a shape that we were dealing with back in Calc 3 when we did x squared minus y squared equals z squared. It would be parabolic in one direction, not parabolic, elliptical in one direction and hyperbolic in another direction in terms of a 3-dimensional shape. So, all right, what is my first step here? Yeah, g of x, y, z. So what is my constraint equation? X squared minus y squared plus z squared minus 1. Okay, step 2. Gradient of f. So, gradient of f is going to be what? 1? Negative 1? Negative 1. How friendly was that? How about the gradient of g? Perfect. Everybody good so far? Okay, so the next step is to do the gradient equation with lambda in it. And like I said, what this really boils down to is component-wise. So component-wise, I have 1 equals lambda 2x, negative 1 equals lambda negative 2y, and negative 1 equals lambda 2z. And the goal is to eliminate lambda. So what I'm actually going to do is I'm going to solve each of the equations for lambda, okay? And we're going to recognize a fact at that point. So the first one, what does lambda equal? 1 over 2x, right? How about the second one? What will lambda equal? Is it negative?
1 over 2.
It's actually going to be positive because it's negative on both sides. And the last one? That one will be negative 1 over 2z. So since the lambdas all have to be the same, this means that 1 over 2x has to equal 1 over 2y, has to equal negative 1 over 2z. I know you're not sort of, I don't want to say comfortable, that's not really the idea, but we don't do a lot of triple inequalities with things. But if these are all equal, and they are, then what do we do next? Or what can we recognize about x, y, and z? X is equal to y, and it's equal to negative z, exactly. You can think about that by taking the reciprocal of all three if you want to think of it that way. You can think about the fact that they all have 2's there, so that's sort of a constant that they all have in common we can eliminate. Or you can just flat out look at them and say, look, everything's the same except they're all in the denominator, so they all have to be the same thing except for that negative there on the end about the on z. So. All right, so we're going to now use this information, and we're going to be doing step, which one are we on? 4? Are we on step 4 in the constraint, right? So inside of the constraint, this is my constraint up here. X squared minus y squared plus z squared equals 1. And we just found out that x equals y equals negative z. So you get to pick your favorite variable. Do you want to use x's, y's, or z's? X. Okay. So that means that everything's going to turn into something that says x. So the x squared will stay the same. The y squared will become x squared. And then the z squared will become what? Yeah, actually it's negative x and then quantity squared, which will then be x squared, right? because this says that z would be equal to negative x. All right, so the first two add to 0. The last one actually just is x squared. So what is x? Plus or minus 1. Now let's use that information with these equations over here to get our point. So if x is positive 1, y would be, and z would be, right. If x is negative 1, y would be, and z would be positive 1. So I have 2 points, 2 ordered triples. And what do I do with them? I plug them into my function. Whoops. My function, f of x, y, z, was x minus y minus z. So we're going to plug in f of 1, 1, negative 1, and f of negative 1, negative 1, 1. I want you guys to go ahead and plug those in and tell me what you get. What's the first one going to give you? 1? I think so. And the second one? Negative 1. So what can you tell me about maxes and mins? Right. Perfect. Any questions on that one? All right, I'm going to put the homework back up in case you want to write it down or didn't write it down last time potentially.